Alright, 5.1, Extrema on an interval. Uh, we should probably start by defining what Extrema is before we get too deep into it. This whole chapter, just to kind of emphasize, is about different applications of derivatives. Okay? Uh, one of them is it helps us with analyzing our graphs. Okay? When we graph, there's a lot of information we can find. And using derivatives is one thing we can do to better accurately tell what a graph is doing. So, in order to define extrema, let f be defined on an interval I containing c. Just reading what I wrote right here. Might be a good idea to pause and write this stuff down. And then if this happens here, we can define a minimum value as f of c is the minimum of f if f of c is less than or equal to f of x for all x and I. It's max if, same definition, but if f of c is greater than or equal to f of x for all x and I. Pretty much saying that whatever that input value is, if that's going to get you the smallest output out of all of them, it's going to be a min. If whatever you put into the f of x function is going to be the biggest for the whole interval, that's going to be max value. And if it's the max or min for the whole interval, you might also hear words like absolute minimum or global minimum or absolute maximum or global maximum. Those words you will be heard from time to time as well to describe the max or min for a function. Extreme value theorem. So this is kind of an obvious theorem, to be honest. If you have an interval from 2 points, there's going to be a minimum and maximum. Okay, within that interval, if it's continuous. Okay, if value's going all the way through, there's going to be a min and there's going to be a max on this interval. So if I had, say, the interval from here to here, min value will be whatever that is, the max value will be whatever that is at the end. Okay, there. That's your extreme value theory. All right, relative extrema. So, sometimes our mins and maxes are not absolute, the biggest point at a given interval. But so for calling extreme either relative or absolute, they can all fall into the relative category, meaning that as this definition states, if there is an open interval containing c on which f of c is the max, then f of c is called a relative max of f. Or you can say that f has a relative max at c comma f of c, the ordered pair. Same thing for the minimum. If there is an open interval containing c on which f of c is a min, then f of c is called the relative min of f, or you can say that f has a relative min at c comma f of c. Because sometimes our graphs, as you have seen many graphs through our time, could look something like this, for example. And we could say that we know that's going to keep going up forever, right? But right here, if we had the interval from here to here, the relative max would be right there, right? That's still an important point we want to know so we can know when it changes from increasing to decreasing, right? So that's where we can call this a relative max. And down below here would be a relative min for a given interval. You might also hear me call it local instead of relative. I got brought up calling it local extrema. But I think your book and your homework will be using relative a little bit more frequently, but they're interchangeable. So if you hear me say local is another way of saying relative extrema. So let's find the relative extrema of this graph. This is kind of jumping to our definition of a critical number as well, and in the next definition after we do the examples, because all we really need to do is we find a derivative. This is nifty. So we find a derivative. Let's do the first one here together. So we find a derivative, 4x to the third minus 8x. set it equal to 0, what values make this 0? Well, that's why we did factoring at the beginning of the year and all that fun stuff. Because we found a GCF, set them equal to 0, so x equals 0, and x equals root 2 and negative root 2. And to find the y value at those points, plug them into the original equation, not this one. Back to the original, because we want to find what the output would be. And the output would be 0 for the first one. For the second one, we put root 2 in, you'll get negative 4. You put negative root 2 in, you'll also get negative 4 as well. Now this value right here will be relative max, and these are relative mins down here. Okay, if you were to see the graph, it would be something along the lines of this. Like that. Okay. Now derive the other one. We have to use quotient rule. These rules don't go away. So let's do that. And we're applying quotient rule. Hopefully you remember it. And then simplify 4x squared plus 4 minus 8x squared over x squared plus 1 over squared. Negative 4x squared plus 4. Now, what values make the numerator 0? So, it would be 1 and negative 1. Those will be the values that make it 0. I factored out negative 4 to make it easier and get x squared minus 1 up top, set them equal to 0, and what will make it 0? 1 and negative 1. So if we put negative 1 into the original, what would you get as an output? You get negative 4 divided by 1, which is negative 2. And then if you put 1 in, you'll get positive 2. Okay. Go ahead, if you want to plug in your graph. It's kind of a goofy looking graph, to be honest. This is a relative max, though, of course. This will be a relative min, or local max and local min, depending on what you want to call it. Alright, so here is the formal definition for a critical number that we kind of alluded to in the last problems. Let the function f be defined at c if the derivative f of c is equal to 0, or if f is not differentiable at c, then c is a critical number of f. That's why we set them equal to 0. Your critical number is going to tell you your maxes, your mins, all that fun stuff. Alright, so this is the process for finding the extrema on a closed interval. I'm about to put that up here. Find extrema on closed interval. Alright, so you're finding extrema, let's say like it's from 0 to 5, right? That 0 to 5 is your interval. So here's your process. 1, find the critical numbers of f in a comma b. So what does that mean for us? That means you're going to find a derivative, set the derivative equal to 0, and find out when it's equal to 0, or when it's not differentiable, right? So one of those two things. 2, evaluate f at each critical number in a comma b. So similar to what we did earlier, right? So whatever those values are, after you found a derivative and set equal to 0, those values, you plug it back in the original. Okay, evaluate it. And then after you do that, for step 3, you're doing the endpoints as well, because the endpoints could possibly be a max or a min. Okay, and then the last step, look at the endpoints, look at your critical numbers, and your whatever has the biggest output will be your maximum. The smallest output will be the minimum. That's the process. Okay, and we'll be doing some of these together right now. All right, so we're gonna find the absolute extrema on this interval. So step 1, as we said, we need to find the critical points. So derivative, set equal to 0. There's a derivative, set equal to 0. Factor out of 3, make our life a little easier. And would you look at that? It would be 2 and negative 2 would make this 0. Is negative 2 in our interval? It is not. 2 is, though. So 2 is going to be the only one that we can use. So we're going to be evaluating f of 2, which would get us 8 minus 24 is negative 16. And for the next step, we have to evaluate also the endpoints. So 0q minus 12 times 0, which is 0. And then f of 4 which will get you 16. So, what is the absolute min and max of this closed interval? So, what's the smallest? That would be f of 2. So, your min is 2 comma negative 16. Your max, what's the biggest, is positive 16. So, 4 comma 16 max. Alright, last one together. So let's find all of your absolute extrema from -1 to 1 of this function. Remember, the third root's just like saying to the 1/3 power. So when we differentiate to find the critical values, 1/3 goes up front, subtract 1, so it'll be -2/3. So it would be 1/3 times x to the 2/3 power. So there's no value that's going to make this 0. But there is one value that will make it undefined, and that's 0. Okay? So x equals 0, we need to check out 2, as far as since it doesn't exist there. So when we evaluate the original, f of 0, or it should be g, because it's g of x as a function. So g of 0, your output would be 0, because the third root is 0, 0. And we've got to do the endpoints too, right? So, g of -1 will get you an output of -1. Third root of -1 is -1. You can find the third root of a negative number, remember. Third root of 1 is 1. Okay? So, what is going to be our absolute min and absolute max? Absolute min is -1 comma -1. Absolute max is 1 comma 1. Those are your solutions. Appreciate you. Thanks for watching, and we'll see you later.